Okay. Yeah, thank you very much. Welcome back to the 13th Radio Astronomy Winter School, organized by NCRA and IUCA. It's my pleasure to be able to present about pulsars at this meeting. Thank you to the organizers for inviting me to participate. Um, okay, so let's get going. You can ask me questions at the end of the talk. Uh, so um, I think you've already heard a bit about neutron stars and about pulsars in general, but here I will give you more like a theoretical overview of why we need radio astronomy and other methods of observation to complement our understanding of theoretical physics behind pulsars. As you probably already know, the story of pulsars began with this young girl called Jocelyn Bell, who was a graduate student at the University of Cambridge. And she detected some scribbles in the observations from using her radio telescope. She was trying to observe quasars. And so she was careful enough to notice the scribbles. And luckily, there was some groundwork laid before this discovery, and it was the following. In 1931, Chandrasekhar had already shown that massive stars may collapse, and 1932, Chadwick discovered the neutron. However, neutrons were already predicted earlier by Majorana, but these were not published. Bardi and Zwicky then introduced the concept of neutron stars, comprising of these neutrons, in 1933. Then Oppenheimer-Volkoff computed the structure of neutron stars using general relativity, and this came in 1939. After this, Jocelyn Bell discovered pulsars, and this was in 1967. Just following this, Gold and Pacini proposed a basic lighthouse model to, uh, to describe these objects. So it was now understood that pulsars are nothing but rapidly rotating neutron stars. So what happens is that there is a beam of electromagnetic emission along its poles, which sweeps the Earth like a lighthouse, and therefore we observe the very periodic pulses. So that's why they were first called pulsars. To understand how pulsars are formed, probably you've already had a lecture about this, but very briefly, if we try to understand the evolution of stars. For the case of our the sun is a very light star. So what happens is the sun keeps burning, it keeps glowing because in the sun there is hydrogen which is burned inside its core, which produces thermal pressure, and this pressure supports it against gravity. But what happens is for more massive stars, like about 8 to 10 times that of the sun, this process continues to form heavier and heavier elements. So you must have seen the periodic table. So in the periodic table, you form heavier and heavier elements by fusion of such elements until iron group of elements is formed at the core. But if you know, so we already know this from nuclear experiments, that the iron group of elements is the most stable. So if you see this binding energy per nucleon against the number of nucleons, you see that the iron group lies at the peak, which means that fusion of iron will not produce any more energy. And what happens at this phase is that there is no more thermal pressure support to keep the star from collapsing onto itself. So this is a very energetic process. What happens is this entire star now collapses towards the center, and ultimately it hits the nuclear energy, nuclear densities, and there is a rebound throwing out the outer layers into the interstellar atmosphere. And normally, this should result in a collapse. So this is what Chandrasekhar had first suggested. But there are some quantum effects which can halt this process. And we know that neutron stars are comprised primarily of neutrons, right? So neutrons are actually, so if you've had a course of statistical mechanics, you might know that neutrons are fermions, and fermions have a certain property. So kind of like this social distancing that we are observing now, so they also have a kind of social distancing, and which means that they always repel each other in their energy levels. Unlike bosons, which can all go to the same energy state at the lowest temperature, in the case of fermions, this doesn't happen, and they occupy only, so one particle can only occupy one energy level at a given time. So this is something that is typical of fermions, and this is called the Pauli exclusion principle.
Energy
And because
state
of this, there
at
is a
the lowest
pressure
temperature.
which is produced, and this is called the degeneracy pressure. So this repulsion or this pressure now can support the star against collapse, but at a radius of only about 10 kilometers. And this is what we call a neutron star. And for stars which are, so the normal stars which are even heavier than 8 to 10 times that of the sun, even this neutron degeneracy pressure is not enough to support it against collapse, and then it collapses into a black hole. So there is an animation here. Can you see the animation? I hope you can. So here, this is a normal star which is going through its fusion phases until it produces iron at the core, and then this stops, and now the outer layers explode towards the exterior, and the core forms a rotating pulsar. So this is what we understand about the formation of pulsars. As I mentioned, the outer layers of the this collapsing star, they explode into the interstellar medium, forming a beautiful nebula that you can probably see if you go through websites like that of NASA. You will see beautiful images of core collapse supernova and supernova remnants where these pulsars are found. So this is what we understand about the formation of a neutron star or a pulsar. So basically, pulsars are compact objects which are formed at the endpoint of evolution of massive stars that end in this core collapse supernova explosion. We also know from these radio observations of these pulses, very periodic pulses, that there are different types of pulsars which are also isolated or in binary. So for example, there are rotation powered pulsars, which means they are basically the energy is provided by magnetic field, which is very strong in the case of pulsars. There may also be pulsars in binary with a companion, where these pulsars actually, because of their strong gravity, they start to suck up material from its companion, and these are accretion powered pulsars. And after the accretion powered pulsars, there can also be a phase when the other the other companion also goes supernova, and there are a bunch of a couple of or a binary of pulsars. So to understand the population, it is a good thing to look at the plot of the spin period of a pulsar versus its spin derivative. So we can actually map all these different types or families of neutron stars or pulsars on this diagram. So you can see that the normal pulsars, these little squares or circles, I don't know what it is, I think little squares, so these cluster around this center, right? So here there are different lines which show you the corresponding magnetic field and characteristic ages, and these are calculated using the magnetic dipole formula. And this comes from a very easy back of the envelope calculation, which tells you that the luminosity of or the spin down is caused by that of the dipole magnetic field. And you can also calculate the characteristic age of these. And from the different clustering of populations of pulsars, we can also understand a little bit about how these are formed. And so interestingly, not only are there pulsars and pulsars in binary, which you see around the bottom left corner in this figure, there is also a population around the very extreme values of period and period derivative. So if you do again a back of the envelope calculation, this tells you that these clusters of pulsars are actually extremely magnetic. So these are above, you can see 10 to the 15 Gauss. So normal pulsars have magnetic fields around 10 to 10 to the 12 Gauss. But this family is extremely magnetic. And these are called magnetars because they are so extremely magnetized. Again, there are different classes of them. Some of them are soft gamma ray repeaters because they show repetitions in gamma rays. Some of them are anomalous X-ray pulsars because they show, again, X-ray flares and outbursts and so on. But in general, they are the observations indicate some common features which indicate that they belong to the same class of family, same class of objects called magnetars. Um, what is interesting about pulsars is that not only radio frequencies, pulsars can be observed throughout the electromagnetic spectrum. So you must have heard about observations of radio at radio frequencies like with which we are expecting from the upgraded GMRT and SKA and so on. In addition to that, we have, thanks to our to the advance of technologies, we have now a vast array of ground-based and space-based telescopes which can observe pulsars throughout the electromagnetic spectrum. So at microwave, infrared, visible frequencies, X-ray, and gamma rays. So some of these are already in uh, are active, and some of them are planned missions. So just to give you an example, this is a very well observed nebula called the Crab Nebula. And you can see that the same nebula at different frequencies. So in radio frequencies, you just saw that the features are not very clear. However, at X-ray frequencies, we can see the inner compact object or the pulsar inside the nebula. So these multi-frequency, multi-wavelength observations, so radio, in addition to other frequencies, actually help us to understand a lot of different features of pulsars, their wind nebula, their formation, and so on. So we can have a complete understanding of their features and their formation. So from all these different observations, so from radio to X-rays and gamma rays, we have actually a lot of different observables, different features about neutron stars that we can derive from these astrophysical data. So first of all, you know that like Jocelyn Bell had observed these very periodic pulses, we can determine spin frequencies very, very accurately. So these are one of the most accurate astrophysical observables related to neutron stars. So spin frequencies have been shown to be around up to 700 hertz for pulsars. Magnetic fields, as I told you, typically they are around 10 to the 12, but for the certain class of magnetars, these can be even up to 10 to the 15 to 10 to the 16 Gauss at the surface. Masses of neutron stars have been, observational data indicates that masses are around 1 to 2 times that of the sun. And the radius typically of neutron stars is around 10 kilometers. So a very simple calculation will show you that if you divide the mass by the volume, so from the radius you can calculate the volume. So this will show you that the densities in the interior of neutron stars is extremely large. So these are one of the densest objects in the universe. And not only, so I will come to the inner structure of neutron stars in a few slides, but to give you an understanding, so nuclear experiments, they probe around nuclear densities, right? So these are some of the densest objects that we see in experiments. There are also accelerators which can go up to higher densities, so a few times nuclear density. In the interior of pulsars, these densities go up to 10 times that of nuclear density. So there is no terrestrial experiment, that can reproduce these kind of conditions. This is why neutron stars or pulsars are also called cosmic laboratories. So they are like laboratories to understand cold and dense matter. So like I mentioned, cold. So this is because the temperatures of neutron stars are extremely low compared to the typical energies of particles that are constituent of these objects. There are also some other observables which can be derived from neutron stars, like, for example, the moment of inertia. And these can also give us some complementary information. Like, for example, moment of inertia is mass and the product of the mass and square of the radius. So say we know the mass and moment of inertia, then we can also determine the radius from these two observations. Also, similarly, gravitational redshift. This is, I will also come to this later. So gravitational redshift is also proportional to mass divided by the radius, and therefore any of these mass and radius complemented by a gravitational redshift measurement can also help us constrain the other. Um, just to give you an example, so neutron star observations can help us determine the structure of a neutron star. For example, the maximum mass. And why do we want to know the maximum mass? So I will come to that. So relativistic binaries in neutron stars, they help us very accurately determine the masses of neutron star. And the reason is that when there are two neutron stars in binary, then we can measure not only the Keplerian parameters, which means you must have read in mechanics that there are these parameters which follow Kepler's laws. But in addition to that, these strong relativistic effects, because neutron stars are extremely dense, they have very strong surface gravity, and therefore they are extremely relativistic. And these show some relativistic effects, and these are called post-Keplerian parameters, and these can also be measured. And from these measurements, we can determine the masses of neutron stars. So you see a chart compiled by Prakash some years ago, and most of these neutron star masses cluster around a value of 1.4 solar mass. Neutron star masses are very interesting to us because this is something that can connect to the internal composition. So on the right, you see a schematic figure which tells you that the equation of state is a parameter. So equation of state is something which appears in statistical mechanics and so on. So it is something which is basically the relationship between the pressure and density. And it is used very often to describe systems, because all these other structure variables can be derived from the equation of state. And for neutron stars, these equations of state can be constructed. And equations of state can be connected to the structure properties like the mass and radius. So I will tell you how in a minute, but just to give you an idea, so this mass radius plots will help us understand what is the internal composition of neutron stars. Particularly interesting are recent observations of some very massive neutron stars, which are around 2 times that of the sun. And these actually start to put some limits on what kind of matter we find inside the neutron star. So let me explain how. So this is also a phase diagram. So like you know that like water, ice, so different phases of water, different phases of matter can be represented by a phase diagram. Also nuclear matter can be represented by a phase diagram. And this we are doing to understand why we need neutron stars and why they are so challenging theoretically to explain with our current understanding. So you can see that this phase diagram, the x-axis is that of densities and the y-axis is that of temperature. There is also another axis. So this is basically the difference between the number of neutrons and protons. So for example, think about nuclear experiments. So in nuclear experiments, matter is at nuclear densities it is cold, it is at zero temperatures, and the number of neutrons and number of protons are almost the same, except for some very extreme types of nuclei which are very rich in neutrons and so on. These can also be constructed in the laboratories, but in general, the neutron number and proton number are pretty close. So in that case, you see that at the bottom figure, you see nuclei or nuclear experiments denoted close to the saturation density of matter, nuclear matter. On the other hand, you see that there are all these arrows marking the heavy ion collision experiments. So these are experiments which are performed like at large accelerator facilities, like the one you have the Large Hadron Collider and relativistic heavy ion collider. You have heard of CERN facility and in Geneva. So these experiments probe matter which is hot and dense, because there are in the accelerator there are these ion beams, heavy ion beams, which are bombarded against each other, producing very high energies and hot and dense matter. So these densities are a few times that of nuclei, and it is also hot. So these occupy more or less this region of the phase diagram. On the other hand, neutron stars, they are cold and very dense. So they go around up to 10 times that of saturation density and cold. So these are actually lying in this bottom part of the figure. And they are also extremely rich in neutrons and poor in protons, right? So they are along the z axis as well. So this means that although we can have some understanding of what happens inside neutron stars, but we also need some additional information which we don't have. So we need to know what happens when you extrapolate to finite to such high densities, and also to this asymmetry, this neutron proton asymmetry. So this is something which is done theoretically. However, there are a lot of disagreements among these different models. um, the current understanding of the interior of neutron stars is more or less like this. So let me go back to the previous figure. So we more or less agree to the fact that in these heavy ion collisions at around 2 to 3 times saturation density, there are some strangeness containing matter produced. And the reason is that nuclei are comprised of so if you have heard about so some particle physics, I don't know if you've taken particle physics courses, but uh, the neutron, protons, electron, so neutrons and protons are in turn made up of quarks, and these quarks are also having different families. Like the lightest ones are up and down quarks. So in general, in nature, in earth on earth, we find these up and down quarks comprising of all these so neutron, proton and elements, right? On the other hand, at such high densities like those which appear in heavy ion collision experiments or those in neutron stars, these heavier quarks start to appear. So the first heavy quark is that of the strange quark, and this strange quark so makes new kinds of particles. So like neutron, proton, there are hyperons which are produced, and these hyperons have been seen, hyperons, kaons, these kind of strangeness producing particles have actually been seen in these heavy ion collisions which occur like at CERN and so on. So these kind of experiments. So now we expect that they should also appear at the high densities which are there in the neutron star interior. So let's put together all the information we have from nuclear experiments and heavy ion collision experiments to understand what is happening inside the neutron star interior. So let's take a cross section of the pulsar, and let's go from outside towards the inner core. So at the surface, so the density increases rapidly from the surface to the interior. So at the surface, neutron stars contain mostly nuclei, and these nuclei are like iron nuclei, so iron family. Then and they also have some embedded in electrons. The whole system is charge neutral, okay? So as we go towards the interior, what happens is this nuclei, as the density increases, the nuclei, the nuclei that appear become more and more neutron rich. So you can see on the cross section on the right that these so as we go from the surface towards what is called the outer crust, you see more and more neutron rich nuclei embedded in a sea of electrons. Then at a certain point, these neutrons become so the nuclei become so rich in neutrons that now these neutrons start to drip out of the nuclei. So this is called the inner crust, and the density is called the neutron drip density. Beyond this, what happens is now actually still under debate. People are trying to understand this with molecular dynamic simulations and so on. So what happens is that these, under the extreme densities, these nuclei start to be deformed in a variety of shapes. And these shapes actually are really funny shapes. So they start to look like spaghetti and meatballs and cheese and like look like pasta. So they are called pasta phases. And then finally, what happens is the density is so high that the entire inner crust now melts into a homogeneous fluid. And this is called the outer core. So the outer core comprises of mainly neutron fluid, but there are also a small fraction of protons and electrons because of charge neutrality. So we always need a charge neutral neutron star. Now, as I mentioned, we have some hints about what lies in the inner core, but you see the question marks in the figure. So the reason is that this is still under debate. So there are nuclear physicists, particle physicists trying to understand what is going on at densities which are beyond that of 2 to 3 times, going up to 10 times. So there are lots of different models. Some say there are hyperons and there are kaons, so these strangeness containing matter, which we see briefly in accelerators. Some say that no, at such high densities, we can even have complete quark soup. And this quark matter can again have a variety, like a zoo of different kinds of phases, like crystalline phases, and there can be even superfluidity appearing at very low temperatures. So there is we have some theoretical understanding, but then the problem is we don't have a direct method of probing what is going on inside the inner core. But we can try to understand the internal composition by connecting them to some kind of observable, right? And this is why we need neutron star models. And to give you an example why the maximum mass comes into play here, so you see in the top figure that the black line in this equation of state plot, that of pressure versus energy density, the black line shows you what happens if there are only neutrons and protons along with electrons. So if there were no strangeness containing matter, then we would have a very steep equation of state. It's called a stiff equation of state. And this um, and then if you introduce the strangeness containing matter inside, then it would have a lower slope, and this is called a softer equation of state. And then Tolman, Oppenheimer, Volkov, they had already shown us how we can derive the structure of neutron stars, and this is done by solving a couple of equations. These are basically balance of gravity and pressure. So this now, if you integrate this, you can actually calculate the plot of the mass and the density, or that of the mass and the radius. And now you can see that this steep equation of state corresponds to a higher mass, and that of the lower, softer equation of state corresponds to a lower mass. So now a very high mass observation like that of the red line can rule out a lot of different models. And the reason is that only those theoretical models which satisfy this observational constraint will now be allowed. So all these different models you see that lie below the line are now ruled out. So this is a nice way of using observations like those coming from relativistic binaries and so on to understand what kind of matter you have in the core of the neutron star. Constraining the radius, however, is much more complicated. So you see in this figure that the mass was a very good tool to rule out models, but then radii, as you can see, that the radii are really varying very widely, right? So we know that they are of the order of 10 kilometers, but then if the uncertainty is this large, then we are not able to put constraints on the models. So there, what is the problem with constraining the radii? Probably you have already heard some lectures about this. So the problem is that there are some uncertainties in observing. So neutron star radii are usually calculated from the thermal emission from the surface. The problem is that we don't understand the atmosphere, the composition of the atmosphere that goes into the model. And the other uncertainty also comes from the distance to the source. For some sources, like those in globular clusters, we know more or less what the distance is. But even then, the atmosphere might introduce some uncertainty. So the radius is definitely much less well constrained than that of the mass. There are some other observations that can help us put some constraints on radius. Like I mentioned earlier, the gravitational redshift. So you see on the right hand figure, there are these absorption features that are seen in the spectra, the thermal spectra, and these can also help us understand, because these spectral lines, from these spectral lines, we can determine the gravitational redshift. And the gravitational redshift actually, so if you see the calculation, it is related to the compactness of the neutron star. And compactness is the ratio of mass to the radius. So if we know the mass of the neutron star and we observe spectral lines, from this we can calculate the redshift and therefore the radius. This is an indirect method of calculating the radii. Recently, there has been a very, so we have some hope of constraining the neutron star radius up to very good accuracy. So hopefully up to 5% accuracy. And this is with the launch of the recent mission called NICER mission. So this is the Neutron Star Interior Composition Explorer, which was launched last year. And this has already started giving us interesting constraints. So this is done by modeling general relativistic effects on pulse profiles of rotating hotspots in neutron stars. So this also gives us the redshift, and therefore it has started giving us some constraints on the radius, but hopefully in the near future, we will be able to have much better constraints on the radius, and therefore also on the better understanding of the interior composition of neutron stars. So this is what we have from different multi-wavelength observations of neutron stars. There is one observation which has opened up an entirely new window to understanding neutron stars, and this comes from the recent discovery of gravitational waves. And this is a very, very exciting new field. The reason is that so gravitational waves were predicted by Einstein when he proposed the general relativity theory. Um, Back in already in 1975, you see that there was an indirect observation of gravitational waves from pulsar binary, which was done by Hulse and Taylor. That's why the pulsar is called the Hulse-Taylor pulsar. And so how did they do that? So they measured the change in the cumulative shift of the, so there is a gravitational effect, a general relativistic effect that they measured from, for example, you see the cartoon on top, you see the animation on top. So there are two pulsars going around each other. And what happens is, as they emit gravitational waves, they lose energy and they come closer and closer together until they merge. So this change in the trajectory of the neutron stars was first measured by Hulse and Taylor, and they showed that it exactly follows the prediction by Einstein. So this was the first indirect prediction of gravitational waves from neutron stars, and which is why they won the Nobel Prize in 1997, was it? I don't remember anymore. So So gravitational waves. So what are these gravitational waves, and why do we look forward to observing them? So the reason is that neutron stars, as I told you, they are extremely relativistic objects. So they are so compact that they bend the curvature of space-time around them. Black holes are even stronger, but then black holes also produce gravitational waves. But we are more interested in understanding neutron stars. So what happens is these kind of compact objects, they bend space-time around them. And if there are any kind of ripples produced in this space-time, it could be because of some perturbation or because of binary motion. In that case, these ripples are propagated, and we want to observe these gravitational waves. The reason is that the gravitational waves actually are like messengers from the center of the neutron star. They carry information about the interior composition of the neutron star. So this is the only possibility of observing something which is related directly to the inner composition. From the prediction of gravitational waves by Einstein until today, there was a lot of hope in observing them, but the problem is that they are extremely challenging to observe because they are very, very tiny waves, which the amplitude is about 10 to the minus 22. So this is very, very minute, and it would be a technological challenge. It's absolutely, this is phenomenal that to be able to achieve something of this precision. So finally, the first gravitational waves were observed very recently. And in the first time in 2017, gravitational waves from binary neutron stars were observed. And this is called GW 170817 because it was observed on 17th of August. And so the feature that was observed by the observatories, like that of LIGO in the US, so the feature was that you see on the cartoon on top. So there is an in spiral phase, which means that the neutron stars are going around each other. And this becomes faster and faster until they both merge. So this is called the merger. And ultimately they merge into one wobbling object, which can be hyper massive. So it has a lot of strange features like very high temperatures, and it could be it could be like ringing like a bell and slowing down. So this is called the ring down phase. And there are a lot of different oscillations going on in this post merger remnant phase. So, what is interesting for us? So, I work mostly on theoretical understanding of the interior of the neutron star, and for me, this is fantastic because, like I mentioned, this if I go back to this animation, you see that these neutron stars, when they are merging, they distort each other because of their strong gravity. And this is like tidal deformation, like almost like these tidal interactions between the Earth, Moon, and so on. So these tidal deformations are actually interesting from the point of view of theoretical physics, because the tidal deformations depend on this equation of state of the interior. So the tidal deformation denoted by lambda that you see in the equation on the right, it was shown to be related again to the compactness of the neutron star, or inversely to the radius also, we can say. So you see a plot from 2018. So this was an analysis of the data. There has been reanalysis of this as well, and we are getting better and better constraints on equation of state from these studies. But what we now understand is that uh, which configurations are more favored, the more compact ones or the less compact ones. And this information comes from this tidal deformability that is related to the merging of the neutron stars in the binary. Um, all right. So yeah, we already talked about binary neutron stars and how they produce gravitational waves. But is it true that only binary neutron stars produce gravitational waves? This is not true. Gravitational waves can also be produced by isolated neutron stars. So Actually, gravitational waves can be produced by any kind of time varying quadrupole. Quadrupole means that you see this animation on top. So this kind of a motion. So you see a ring of particles here, and if gravitational waves pass through such a ring of particles, it would be distorted in this fashion. So this is in this xy direction. There can also be other polarizations. So in other directions, say 45 degrees to this. So this kind of a time varying quadrupole motion can produce gravitational waves. So not only neutron stars in binary, but also isolated neutron stars can produce such a time varying distortion. So what can produce this distortion? So rotation, any kind of deformation, some oscillation, so kind of like quakes, like you have earthquakes, you can also have star quakes on the neutron star surface. So all these can produce gravitational waves. To give you an example, you see that this is the rotation frequency of the neutron star versus time. So you know that neutron stars are slowing down because of magnetic braking. So generally they would follow a straight line which is diagonal to this curve, and therefore they are slowing down very smoothly, because neutron stars are usually very periodic, and therefore this would be a smooth line. However, there are certain features seen in rotating neutron stars. These are called glitches in the rotation pulse, in the rotation period, which means that there are sudden jumps, and then the neutron star goes back slowly to its original, or to a equilibrium configuration, slowing down again smoothly. So this kind of a glitch would result in what is called a burst source of gravitational waves. So we also, there are, this is much more challenging to observe, but there are currently people trying to build better and better models so that we can pick out these kind of signals from gravitational waves. So glitches is one of them. The other can also be that of flares. So like I already said, magnetars are very strongly magnetized neutron stars, and they can show, so you know about the sun, right? So the sun also, when it goes through solar activity cycles, it also shows like flares and outbursts. Some of you might have also seen the, like, there are these corona features and so on, particularly during the solar eclipse. These are observable. In the same way, because of the very strong magnetic field of magnetars, they also show these kind of flares, and these flares can also produce time varying, because they are also rotating magnetars which are also bursting, and these flares can also be observed as burst sources of gravitational waves. um, Not only that, magnetars, uh, I think my screen, yeah, let me try again. I think Keynote quit for some reason. All right, let me share again. Can you see now? Okay, let me go back to the slide. All right. So I was talking about these gravitational waves from isolated neutron stars, right? So magnetars in general, when they are also very deformed, and the reason is that, so in general, pulsars are quite spherical, because they are. So what happens is that when you have very strong magnetic fields, these pulsars can now be deformed into elongated shapes, and these, when they are rotating, these can also result in continuous sources of gravitational waves. So now these are like continuously varying, time varying quadrupoles. There can, like I mentioned, like earthquakes, there can be star quakes on the gravitational waves. So these can also produce these can also produce gravitational waves. And So there are different sources. There are something called mountains on the surface. Mountain means like a bump, kind of deformation on the surface. This can produce gravitational waves. It's a funny term because mountain on a neutron star, a mountain on the earth would be like the Everest, but on the corresponding Everest on a neutron star would be a few centimeters high, and the reason is the very high gravity. So this would completely crush a mountain to a height of a few centimeters only. So these kind of bumps on the surface of a rotating neutron star can also produce gravitational waves, magnetic fields I already talked about. There can also be these star quakes I was talking about. So depending on, like on Earth also, these quakes are classified depending on what kind of restoring force they have. On the neutron stars also, you can have different modes of oscillation, and these modes of oscillation also are classified depending on what kind of restoring force brings it back to equilibrium. There are fundamental F modes, there are pressure P modes, there are G modes, which are because of some change in density. There are R modes because of rotation, and also there are pure space-time modes called W modes. And these again also depend on the internal composition. For example, what would be the height of the mountain? This would depend on what is the elasticity of the crust. What kind of star quakes you will have. This depends on what is the internal composition, what are the components, whether there are hyperons, whether there are superfluids, what kind of an interface do you have between the solid crust and the liquid core. All this will affect the gravitational wave spectrum that we observe. So, as I mentioned, it's a huge technological challenge to be able to detect these little features in the gravitational waves. But such detectors have been built already across the globe. The LIGO detector, the first one, had only reached the design sensitivities, but then it was the advanced LIGO, the upgraded version of LIGO and Virgo, which first detected the gravitational waves. LIGO is in the US, at Hanford and Livingston. Virgo is at the border of Italy and France. One of the detectors from LIGO is planned to be moved to India, and this is going to be called the LIGO India project. You might have already seen on social media. So LIGO India project is an upcoming mission which will complement this global array of the second generation and third generation detectors. So there are also other planned missions like the Einstein telescope, the Cosmic Explorer, and so on. And all these will give us information about these different burst and continuous sources that I talked about. Finally, I will mention this curious case of the gravitational wave GW170817. And the reason is that this has opened up an entirely new window to the universe. So not only have we observed gravitational waves from this, thanks to this global array of detectors which scan the sky in radio frequencies, X-rays, gamma rays, and so on, we have detected many different features. We have collected a lot of information about these objects. So the VLA detector gave us information about the radio frequencies. So the gravitational wave GW170817 from the at radio frequencies. The gamma rays from these objects were collected by the Fermi and Integral telescopes, which are space-based telescopes. Not only that, X-rays were also picked up by Chandra telescope, and the X shooter on VLC also told us that about the kilonova. So there are different theoretical models, explanations of what actually happens during this binary merger. And it is thought that the optical spectrum shows a very energetic burst. So this is called not a supernova but a kilonova. And then we also think that the heavy elements are produced in this kind of an in a scenario like this, so all these different theoretical models were at once confirmed at the same time by just one observation. And this opened up a completely new window to the universe and a new way of understanding astronomy. And this is called multi-messenger astronomy. So this is a combination, a collaboration of theoretical, observational, and in observational also a multi wavelength, multi frequency, multi messenger. So gravitational waves, radio waves, x-rays, gamma rays, and so on, so all of them put together, it's like a jigsaw puzzle where we put together information from all these different sources, and it gives us a complete understanding of what is going on in such a system. So we are looking forward now to more such collaborations, so not only radio astronomy but along with theoretical understanding of the different features and across the electromagnetic spectrum, gravitational waves put together to tell us more about what lies inside the pulsars. Finally, just to give you a picture about the latest discovery. So this is a picture where you see that not only black holes, but in addition to the electromagnetic neutron stars that you see at the bottom of the figure, there are now these LIGO Virgo neutron stars which were discovered in gravitational waves. So we are having a better and better picture of the neutron stars and understanding of their interior composition, of the population, their relation with black holes, and so on. And finally, the last word of hope is that LIGO India project is coming up now. So this is a planned mission, like I already mentioned, which will complement the other 3D detectors which are in action right now. So along with LIGO, Virgo, GEO in Germany, and Kagra, which is now operational in Japan. So LIGO India will give it a better resolution, better position to be able to give us even better information about pulsars. So I will stop here. Thank you very much. And please feel free to ask questions.
Hi. So, are magnetars pulsars as well, or just normal neutron stars?
So magnetars are so uh, pulsar is a generic name for neutron stars, right? So magnetars are neutron stars. Pulsars are those which from which we observe regular pulses. So pulsars are a subset of neutron stars which show pulsations. So this could be not only in radio frequencies but other frequencies as well. Magnetars may or may not be pulsars because they may or may not show pulsations, but they are neutron stars. And they show some other features, like I mentioned, for soft gamma ray repeaters or for X-ray, anomalous X-ray pulsars, they show some additional features which tell us what is the magnetic field. But they are neutron stars, but not all necessarily are pulsars.
Thank you.
Yeah, you're welcome.
Hello.
Yes.
Yeah. Hi. So I wanted to ask whenever two neutron stars collide, their
Mhm.
cores will get disrupted, and hence all the strange quark matter which is inside will get dispersed into the ISM. So can we implement some indirect observational method to study those quark elements?
So this is not entirely true. So what happens is when you can actually see this animation, what happens. So I'll put the video just now. So what happens is that what is expelled in the outer interstellar medium is actually only the outer light layers, but the core of the neutron star, which is the two neutron star cores, they actually fuse to form another core of another hypermassive, supermassive, we don't know exactly, it depends on what kind of neutron stars there were, but this will form a post-merger remnant. So this remnant could be a black hole, this remnant could be a wobbling neutron star, which finally settles down into a neutron star or it collapses into a black hole. But this it's kind of, imagine, like for example, in even in biology probably you have this kind of an example, right? So you have nuclei which are dense surrounded by the surface layers. So these nuclei which are like the cores, so these fuse to form form a massive one. So this does not get dispersed. This is extremely dense. So this does not get dispersed. This can either collapse or it can remain like a wobbling neutron star or settle down into a normal neutron star. So I think if I put the video, this will be more clear. You can see these are the neutron stars going around each other, then they fuse, and then you see that the core remains there. The outer layers get dispersed. This is why we see all these electromagnetic emissions, but the core actually remains at the where you see this peak in the gravitational wave spectrum. It's also called the chirp frequency. I hope this is clear.
Yeah, it's clear because we don't yet know the interaction of this kind of matter with normal matter, right? So, I mean, how
Uh,
will, if it is released strange matter, then how will it react with the other medium
we
in
have a
space?
little understanding. For example, this is also what happens when you have an accelerator. So in an accelerator you have these heavy ion beams and you are fusing this also produces a ball of fire called a quark gluon plasma, and then this hot matter finally attains equilibrium and then cools down. So we know a little bit, what we have an expectation of what will happen, but then exactly which components are present and which components are forbidden, this is something that people are still speculating.
Okay, yeah, thanks.
Hi Devrati. So
Hi.
there's a question from YouTube. So Ritvik
Mhm.
Mahadak is asking how we change the gravitational wave in audio signal so that we can hear the sound of two colliding black holes or neutron stars.
Oh, this is actually already done. If you go to the LIGO website, you will see, for example, for the GW1708 as well. I think I might have it on my computer. If you want, I can try to play. In fact, for the chirp signal, do I have? No, I don't have it here. But let me try if I can find. It is possible actually to. Okay, I have it for another one. I think this is 150914. This is another GW effect. Let me know if you can hear this. Could you hear that?
No, actually.
Okay. Uh, let me see if I can embed this here. Can you hear it? Could you hear
Mandir
it?
maju.
No, it
Okay.
was not
If
audible
you go to
properly.
the LIGO website, you can actually hear these frequencies, which have been converted to audio.
Yeah, thanks.
Hello, ma'am.
Yes.
Uh, yeah. So it was a nice talk.
Thank
So,
you.
ma'am, I have a question that you showed us the possibilities of detecting the GWs with the neutron stars using LIGO. Ma'am, as we know that in the coming years, LISA will be also be operational, the space-based detectors. So, what
Mhm.
are the advantages we can expect from it on detecting the neutron stars using the
Uh,
space-based
let
detectors?
me play this slide so you can see the slide, right?
Yes, ma'am.
So here you can see this is, I mean, this is a schematic figure. Now this has been improved a lot more. If you go to the LIGO or LISA web pages, you can see the upgraded version. But to give you an idea, so this is the sensitivity curve of gravitational waves and the different frequencies. So you see that LISA lies here. Okay, this is 10 to the minus 3 to 10 to the minus 1, and you see LISA is active in this region, and this is where you have the black hole mergers and so extreme mass in spirals and so on. On the other hand, you see the neutron star coalescence and the rotating neutron stars are at higher frequencies, right? So this is where the advanced LIGO found them. And so I mean, LIGO India and the upgraded, so LIGO and Virgo detectors are sensitive at a different frequency band than that of LISA. So LISA will help us understand black holes, and also if there are like black hole neutron star binaries, we probably will be able to distinguish them from those of pure neutron star binaries. But then, like I said, there are other Even the Einstein telescope, this will be able to give us information about neutron star, but not LISA exactly directly.
Okay, thank you.
Hello, ma'am.
Hello?
Ma'am, so I wanted to ask about the modeling of these neutron star mergers. So you mentioned that the observable being these gravitational waves, we observe them and then using them we model what these neutron stars are. But
Mhm.
while in the time that these gravitational waves are traveling to us, can't they like interact with other gravitational effects in our line of sight, which may cause them to distort a little? And do we account for those in our modeling, or do they not play that big of a role?
Yeah, this is a good question. I have not actually gone into all the details of the models here because of time constraints. If you like, you can actually go to the LIGO India website. There are these GW at home lectures. I have also given a lecture, and there are also other people who talk about exactly how this is done, this decoding is done, particularly with the help of templates. So it's something called match filtering. So you build these kind of from our current understanding, we developed these different templates, and then you match them with the frequencies, and then you try to find where these exactly match, where these the difference between these two comes to minimum or zero. So from this you try to construct like which part of the spectrum, you try to extract that information. Of course, this is a very complicated task, and you need to take into account a lot of different effects, and it is also not perfect, but there are a lot of details of the modeling which I have not so this is basically coming from the data analysis part. I am not an expert of data analysis. I am mostly into the theoretical modeling of the interior and the structure. So I have not gone into those details, but then if you're interested, please go through these lectures. They are very informative, and you will find exactly how this process is done.
Okay, thank you, ma'am. I had another question. So you mentioned that these neutron stars may have like mountains of a few centimeters on them, and that can like cause these gravitational waves. In
Mhm.
my understanding, neutron stars are very, very smooth objects. So what can cause these centimeter long mountains to emerge in the first place?
Yeah, this is also interesting. Of course, I mean there are some deformations on like the Earth is also not completely smooth, right? So these deformations, the other reason for these deformations, like I mentioned also here, is that there is something called crust cracking. Although it is not yet clear, like I mean these are all speculative models, but then it is thought that the crust itself, it's a solid crust, right? And there are also like depending on the elasticity of the crust, there are deformations on the surface of the crust, and these are what are called mountains. So these deformations of the crust can be caused by different sources, but yeah, and this gives us an idea about the features like the elasticity.
So is this a general feature or a like special feature of some neutron stars?
Yeah, mountains are not found on all of them, but then the elasticity of the crust, like I mentioned, this is a prime factor which controls this. So, of course, I mean, you don't find mountains on all of them, but they may be.
Okay, ma'am. Thank you.
Any other questions, or am I? Or should I stop here? Are we running out of
We
time?
could take one or two more questions, Debarati, I think. Any other questions?
Okay.
And does not,
Hello.
yeah, okay,
Hello.
yes.
Yeah. So I wanted to ask, how do we differentiate between a binary and a single neutron star? I mean, the possibility completely will depend on a line of sight, and we can miss a couple of binary neutron stars as well due to the lack of line of sight.
Yes. So, I mean, there are when there are so you can actually even think of the earth moon system, right? In the earth moon system, when you have binary interactions, you see different things. You can see tidal effects, you can see eclipses. So it's the same kind of thing when you have these kind of eclipsing features, when you have these kind of tidal features, then you know that there is something else that is affecting the neutron stars. um, but I mean there are also other things, like for example I mentioned in this where was it, Right. So I talked about accretion, right? So here also, you see that the neutron star may try to suck up material from its companion. And in the process, there can be flashes like X-ray flashes and so on. So these kind of activities also tell us what kind of interaction neutron stars are having with the surroundings. On the other hand, if you have just a single neutron star, then you will have a different kind of a pulsar wind nebula around it. So you can tell from the electromagnetic, like I said, these multi-frequency observations, multi-wavelength observations give you an idea about the neutron star and its behavior with the surroundings. So we can more or less tell whether it's an isolated system or a binary system.
Yeah, it clears. Thanks.
Debrati, we can probably stop. Usually, we take a gallery shot of every lecture after